all cells have all of the capacities that we grant ourselves. They're cognitive, that means they measure information. They're aware of those measurements. They are sentient. They don't have feelings the way we have feelings, but they have states of preference. We are solutions to cellular problems. It's not good for our egos to think of ourselves this way, but what we are is we are a wonderful habitat. Our kind of intelligence is how we measure intelligence across the scale, but that's not the way biology should measure it, and it's not the way evolution measures it.
This is Brain Inspired.
Hey everyone, I'm Paul, and I am jet lagged. So the first thing I want to say is that I just returned from Norway, where I participated in the annual conference for the Norwegian Research School in Neuroscience. So I just want to say hello to my new Norwegian friends, and thank you again for having me. And I look forward to throwing more axes with you anytime, and or playing with more bows and arrows. I had a really good time, so thanks. All right, as you know, mostly on Brain Inspired, we talk about the intelligence of brains and or models of brains. As you also know, brains are made of neurons, among other cells, and the models that we discuss are made of units that to some minuscule degree mimic real neurons. The key here is that we think of intelligence and cognition as a property of the collective activities of all those neurons and or units. On this episode, the focus is not on neurons per se, but on individual cells of all types. So my guest today is William B. Miller, who has just written the book Bioverse, How the Cellular World Contains the Secrets to Life's Biggest Questions, which is all about Bill's thoughts and research on the intelligence of individual cells, be they neurons, skin cells, bacteria, and so on. Bill's claim is that every cell is intelligent in its own right and has a sense of self in its own right. And these single cells strategically come together to engineer a collective intelligence which makes up each of our bodies. And when I say us, that refers not only to our own cells with our own DNA, but also the massive collection of foreign cells within us that form partnerships with each other and with our own cells, our microbiome. So we talk about all those concepts, Bill's thoughts on cell intelligence versus brain intelligence, the current state of cellular science, which Bill calls the era of the cell, and how he envisions that science revolutionizing our health treatments, and many more topics. So I link to the book and Bill's website in the show notes at braininspired.co/podcast/149. Thank you to all my Patreon supporters and students in my online Neuro-AI course, either of which is an excellent way to support the podcast if you value what I do and or you want to dive deeper into those kinds of topics. For those of you watching on YouTube, I apologize. We couldn't get Bill's camera quite up to speed, so this turned out to be an audio-only episode. Nevertheless, I hope you enjoy listening. Here's Bill. The book is Bioverse, How the Cellular World Contains the Secrets to Life's Biggest Questions. Welcome to the podcast, Bill. Nice to have you here.
Thanks, Paul. I'm really thrilled to be here.
So this book is really a thorough dive into, a deep dive into the individuality of our cells, their intelligence, their networking abilities, and how we are not just our own cells, but we're made up of our microbiome, a huge collection of foreigners. So,
right.
Yes. And it's interesting. I had this reaction, I think it was around chapter 8 in the book, that just swimming in these waters about individual cells and how we're made up of them, I had to contemplate how, I feel like an individual, but in reality, I'm many, many, many individuals. And it's just what a miraculous thing to feel like an individual, and yet we're made up of many individuals. So thanks for making me recontemplate that. And do you, but right now I feel like an individual, but for a moment I felt like a collection of individuals. In your, as you're going through your day, Do you feel like Bill Miller, or do you feel like lots of individual cells that make up Bill Miller?
No, I feel absolutely a singular individual, and that's how it's meant to be. That's the super sauce. That's the amazing seamless collaboration that exists among our cells. I don't know how much your listeners might know about the cellular world. Most people know almost nothing, but we're a specific class of living organism that's best termed a superorganism. We are maybe 100 or more trillion cells, maybe hundreds of trillions if you include all of our microbes. If we included all of our viruses, maybe even more than that. We don't actually know the exact number, but let's just say trillions and trillions that work together so seamlessly that you feel like one person. I wake up in the morning, I look in the mirror, I go, eat your heart out, George Clooney. I am gorgeous. And but once I started studying cells, I realized that each and every single one of those cells is what we term self-referential. Well, what does that mean? It means it's its own actual problem-solving individual. Every single cell, every single microbial cell, every single one of your personal cells, your pancreas cells, your liver cells, your skin cells, every single one of them is a living form, which it's exhilarating and daunting and frightening, because now we have to figure out how is it possible for all of these trillions of cells to work together so well that I'm Bill Miller all day long, and never don't quite feel that way. Although we do have a number of experiences as living organisms that we have never quite understood, and we still don't have the information. But there are those sensations when you're out of body, when you're living on another sphere. You are you've reached an altered mental state, and those may give us clues on how to find out exactly how all of our cells work together so well.
How did you come to appreciate the cell? And maybe you could just mention how you essentially switched careers to study this new-ish love of yours.
Well, I love this question because I can tell the listeners that there is no one that was more surprised than I, that I turned from a contented career in medicine. I was a practicing academic and private practice physician for over 35 years. And I had a passing interest in evolutionary biology, but no more than any ordinary doctor or scientist that has taken that reads generally. It really hadn't been a focus of my concentration. So I'll be quick about this, but I was at a medical meeting for my specialty in medicine, and it involved long days of sitting and listening to lectures. And I can only do that for a certain number of days before I go absolutely nuts. I'm not really a good sitting person.
Days? I can only do it for hours.
I know. It's just, it's for me, the first day is exciting. The second day begins to start the agony. Anyway, so it comes around the third or fourth day, and I've had it. And it's mid-afternoon. I turned to one of my partners who happened to be with me, and I said, I got to get out of here. And we're in Chicago. The meeting is a huge convention center in Chicago. It's a big annual meeting. And I said, let's go someplace. Let's go to the Field Museum or the Art Institute. You pick. He chose the Field Museum. So we played hooky. We go to this museum late in the afternoon. And I don't know how many people that are listening may have been there, but if you walk into the Field Museum, there's this gorgeous, magnificent rotunda that you walk into. And what caught my eye immediately, and is meant to, is I like to say it's a boy named Sue. It's the Tyrannosaurus Rex. It's that magnificent Tyrannosaurus Rex that sits in the rotunda of the Field Museum. And I was startled. Just the scale of it. I'd seen fossils before, but the way it was presented, the skillful way that it was presented, really attracted me. And I walked over to look at it. And that's when everything changed. I started to notice that the bones of the Tyrannosaurus rex have a remarkable similarity to our own. And that just completely shocked me. So let me explain that. Of course, they're huge, and we're talking about an enormous difference in scale, but the major features, the shape of the head of the humerus, that's this bone, or the femur bone, the big thigh bone, the shape of the general shape of the pelvis, ribs, the vertebrae, the alignments, they're different, but the muscle insertions, where the grooves are on the bones for the muscle insertions, were pretty close to what I know from human anatomy. And I was very skilled at human anatomy based on what I was doing for a living. And I didn't know anything really about evolution, but I did know that the general thought was that it was all accidental, that nothing was on purpose. It was always the source of random mutation. And I'm just generally thinking about it and realizing that this was a successful creature for over 6 million years. And then I'm looking at the arms, and those arms are unbelievably tiny. I mean, they just make no sense at all. But the arm bones are very much like our bones. And nothing made any sense to me. And I was just confused and interested. I turned to my partner. I said, boy, I'm not sure that what we were taught makes any sense at all. And he was very dismissive. He's a super intelligent guy. He just said, no, it's all a matter of time. And you're wasting your time to think about it. And for some reason, that became a challenge. That was like a gauntlet had been thrown. And so I decided to start looking things up on the web. It was at a period of time when the web existed, fortunately.
When was
a vital resource.
Was this the 90s? When was this?
This was the 90s, yeah, the late 90s.
Okay.
Very, very late, early 2000s.
So you were searching on like Lycos or something like that, probably.
AOL? I don't know. Was it AOL?
I don't know.
I know my connection. I had the phone, the dial phone was ringing. Anyway, I was able to get articles that I wouldn't ordinarily get from the library, and I did utilize local libraries, including a local university library. And I started to think about it. And one other quick thing, and then we can move on. I had made an observation in my medical practice that mattered to how all this turned out. I was in a field that offered guidance and advice by interpreting imaging for all sorts of specialists. So it would be the orthopedists, it would be the gastroenterology doctors, the neurologists often. And I noticed that we were very reliant in radiology and imaging on patterns, consistent patterns. Some of them were so specific that we could make a very likely diagnosis, almost a certain diagnosis for certain diseases. For example, on an MRI scan of the brain in someone with toxoplasmosis, there's a specific pattern around this cerebral spinal fluid pathways in the middle of the brain. You see that, and you can very closely predict that it's going to be toxoplasmosis. And I started to wonder why. Why could we make that decision? What was it about toxo that brought it to that site? And the feeling among all my partners was, well, they're just like little robots, and they go there and they default, they're circulating around, and they find that spot and they kind of like it, and that's fine. But I said, they like it. He goes, yeah, they kind of like it. Well, that mattered to me. Preference. What has preference? Well, robots don't really have preference. It seems like such an uncomplicated thought, but it actually was a very difficult one for my partners. They didn't want to hear it. They had no interest in it. They're super smart guys and gals. It just was not interesting to them, and it seized my imagination. So what do we know now? Every single one of these cells, every single one of these pathogens is seriously smart in its own limited scale. It's intelligent. What do I mean by that at the cellular scale? They're problem solving. They get a stream of information and they interpret it. They measure it. This is an important idea, that cells are measuring information, because it tells us why we have multicellularity. Why do I exist? Why do you exist? Why can we as a collection of cells in the trillions get along? Because cells measure together to assess environmental uncertainties. Every cell measures the environment and it makes its best guess, and then it deploys its assets. And it doesn't have unlimited assets, just like ourselves. We have to make choices how we're going to spend our energy. We can do this. It's a matter of focus. We can do this or that. We don't have energy for both. So we make a choice. Cells are not different in that way. They have scant energy resources, and they have to deploy it sensibly. They have to solve problems. How do they do that? Well, they learned that they can solve problems better together than apart. And that's precisely why we exist. We are solutions to cellular problems. It's not good for our egos to think of ourselves this way, but what we are is we are a wonderful habitat for exactly those combinations of the trillions of cells, my personal body cells, and the microbiome that we share. And our microbiome as a species is quite specific compared to any other. Mm-hmm. We share certain bugs with other species or other primates and so on. We share certain bugs with our dogs and our cats. But if you take the whole composition, it's very species specific. Going further, it's actually individual specific. You have your own personalized microbiome. It is attuned to you. And why is that? Because they are partners. They are mostly partners. Yes, they can threaten you. There can be pathogens that are lurking. These can be dangerous. But most of the time, all these cells and all of our microbes are getting along just fine. And you couldn't live without them. And they can't live the way they want to live without you. You are their state of preference. And so I'm happy to be satisfied.
I mean, yeah, I learned a lot in the book. One of the things is just how diverse our sort of, I guess you'd call them sub-microbiomes. Each of our organs has its own specific collection of foreign cells. I guess, did you use, is the phrase sub-microbiome in the book? I don't remember.
Actually, I was going to steal it from you because I think it's brilliant. I think that's a good way to put it, because we loosely tend to use the term microbiome for our entire microbiome. But if I talk about my skin, I'll talk about my skin microbiome, my pancreas microbiome. The term submicrobiome might make sense. It would be the pancreas submicrobiome. And I have to think about it. But I think the important point for everyone that's watching and listening to this is this is a very surprising thing. I've been very, very lucky. I had a career in medicine that has spanned now some of the great advances, especially in imaging, which is where I spend a lot of my time. When I first came out of my residency, computed tomography had only just begun. Ultrasound was extremely primitive. No such thing as magnetic resonance imaging existed. Most of the great nuclear medicine procedures that we're using today didn't exist. Almost none of the interventional procedures that I did, a lot of work in interventional work, none of those existed. So I've seen a huge and gratifying progress in medicine. And one of the things that I was taught when I was in medical school, as just a matter of certainty, is that you're sterile on your insides, except for your gut. Your gut has bugs, and they somehow do something, which was not really known. They had something to do with digesting fibers and carbohydrates, but there was no conception that they were a critical part of our metabolism and physiology like we understand today. No one knew that. So I would say to a patient, oh, good news, the antibiotic that you use cures your urinary tract and your urine is sterile. And I really believed that. And it was correct science of that moment decades ago. Well, that's wrong. Your urine is never sterile. But you have gotten rid of the disproportionate amount of the pathogenic bug that was causing you symptoms. So it's a hugely different nuance of understanding of the way thing is. Now we know that it is beginning to become certain that absolutely every part of our body has some constituent microbiome. Some of it is tiny, like our brain has a very tiny microbiome, but it has it. Our pancreas has an active microbiome. In fact, we now believe that it is an active player in cancer. For instance, it is believed that a breakdown of the pancreatic microbiome, that's called a dysbiosis. Everything's got to have a scientific name in what we do. We don't know the answer. We make up a scientific name, and it sounds wonderful because we sound educated anyway. Anyway, this is a good word, dysbiosis, because it simply means that the normal friendly partnership between the bugs that constitute the normal background microbiome has broken down. And that can have many causes. It could be due to cellular damages in our body cells, our pancreas cells, like our insulin cells, for instance, insulin's producing cells, the beta cells, or it could mean that there has been an interloper, an outside microbe that's come in and disturbed the background pancreatic microbe. As it turns out, there is pretty strong evidence that a fungal player causes an inflammatory response in the pancreatic microbiome that somehow, for reasons that we don't yet understand, triggers sufficient underlying cellular changes to induce early stage pancreatic cancer. And how this will pan out and whether future scientific studies will corroborate this absolutely is yet to be seen. But that's the initial information, and it makes an important point. Every part of our body has its microbiome. Testes have a microbiome. The uterus has its microbiome. The lungs have a very important microbiome. It contributes to protecting us from infection, and also it sets us up for the possibility of infection. So someday we may find one way of treating SARS-CoV-2, of COVID, would be to alter the microbiome of the lung rather than necessarily having to wait until you're infected or necessarily have an immunization. Or we may always need immunization. I don't know. I'm just saying that it's a tantalizing prospect in this new era of the cell that we're entering, this new understanding of cellular life, that we stand on the threshold of at least beginning the search for an entirely new ways of combating disease, either preventing it entirely or stopping it at an early stage before it really becomes highly damaging for us. Even the fetus, which we all knew, we all were taught that absolutely every fetus is sterile. The placenta is sterile, amniotic fluid is sterile unless there's a bad bug in there. Well, now we're finding out that that's not the case. The fetus has a very tiny constituent microbiome. The placenta, which is always assumed to absolutely be sterile, probably has its own microbiome. That's still a matter of some debate. And amniotic fluid definitely has some scattered bugs in it, mostly, and is rarely a problem. We're finding, surprisingly, that this microbiome matches the mother's mouth microbiome more than any other body site. We don't really know why exactly that is, but you have to get the data, and then you can kind of work towards finding out new things along the way. Why is this important? It means that from the moment of conception, we are being subjected to the influences of our microbial companions. And even if the number of microbes that a fetus has is tiny, the mother's metabolism is highly dependent on its microbial partnerships. And so the fetus is being bathed by these metabolic products from the get-go. So we're never, ever separated from microbial life. In fact, this is the way I think people should look at it. We are taught, and in fact, even most scientists, even most biologists today insist on talking about the relationships between our microbiome and our cells as us and them. So us is our body cells. They're the special kind of cells. Our cells with our DNA, our specific DNA, they're the specific cells. They're called eukaryotic cells, fancy name. It just means that these are the kinds of cells that allow organisms like us, and they have a nucleus. They have a nucleus, and prokaryotes, that's bacteria, and other types of cellular microbes don't have a nucleus. The end result is it's wrong to look at it strictly as us and them. It's a consensual we. And that's the term that's important here. Consensual we. We're a negotiated product all the time. No matter what is happening to us, we are always that product of the constellation of all of ourselves working together. And it governs our life cycle in ways we have yet to discover. But one of the ways we probably age is that the partnerships break down. What does that mean? It means that cells probably lose the ability to efficiently signal one another. Why that is, I don't know. But the most likely pathway to aging, protecting aging, is to improve cell-cell signaling. It's too new a thought for us to have many experiments in that direction. We're finding out that many of the medications that we rely on are working through the microbiome. Let's take, I'll bet many listeners, people are watching, have diabetes. Type 2 diabetes, adult onset diabetes particularly. Well, one of the most common medications is metformin.
Okay.
It's an excellent drug. In fact, there's some good papers, some good information suggesting that not only does it work to lower blood sugars, but it might be an anti-aging drug. It might protect cognition. There are all sorts of things that drug does that we still don't understand completely. But one thing we do understand now that we didn't until very recently is that it appears that the mechanism of action of metformin is through its shifting our gut microbiome in a way that's improving us. And again, we don't even know those ways specifically yet. It's just that we know to look because we have that information.
So on this podcast, we talk a lot about the complexity of the brain and, the challenges in modeling the brain and understanding it. And as you're talking about, potential treatments by shifting and adjusting the different participants of our microbiomes and our as it were, microbiomes, is there a worry, or do you have a worry that the challenge is could be insurmountable in futzing with such a complex system as our microbiome is, that is just going to be nearly impossible to know how to do? I mean, you're also just talking about drugs, and it was making me think of the medical industry, no knock on you, but how we, just bathe the body in a drug and then, see if it works, right? So we don't really understand what effect a drug is having. And you were just talking about, this drug working through the pathway of the microbiome. So I guess my question is how, and this is kind of an aside, so I apologize, but how optimistic are you that we will understand the shifting complexities of our microbiome enough to be able to know how to treat certain organs or, and so forth, to shift it back into the right place?
It's just a terrific question. And Bioverse, the book that's the reason that you're kind enough to have me on, really goes into explaining exactly the reasons why I am truly optimistic. As I say in the book, we're in what I like to call the new era of the cell, the era of the cell. And I'll explain first what that means and then its ramifications. Throughout human history, we tend to concentrate on battles and politics and religion, religious battles particularly. But when you look at what are the things that have mattered most to the average person, but leaving faith aside, let's not go in that direction today because it's too complicated. What are the things that have really mattered? Well, it's really been medical revolutions. And what kind of revolutions am I talking about? There was vaccination. Before that, inoculation. Before smallpox killed hundreds of millions of people. The smallpox has been virtually eradicated. Polio, another perfect example of a terrible scourge. I'm old enough to remember kids with braces, walking in braces. It was a killer also. I grew up with images of kids in iron lungs. So vaccination was one example of a critical revolution. What's another one? Antisepsis. So that surgical wounds or battle wounds could heal. Anesthesia. Can you imagine surgery before anesthesia? In the book, I describe an operation in Boston in the 1800s and the 19th century, and the horror of it is unimaginable.
Grabbing the tongue.
Exactly. Yeah, you read that. Thank you. So, in all, there have been 6 prior revolutions, including germ theory and imaging, and now we're up to the 7th. I think it's the 7th. It's the ear of the cell. And why am I talking about this in the terms of revolution? Because it radically changes all of how we look at biology, and ultimately it will change how we, as a society, look at ourselves. Knowing that all of our cells are intelligent, and knowing further that we'll rely on a critical partnership with them, forces us to look at research in biology in an entirely different way. So what does this mean? It means that we're going to leverage this actual cellular intelligence, this microbial intelligence, to our own benefit. So we engineer. It's obvious that we cooperate. We measure together and we communicate. And because we can do those 2 things, we can engineer. That's why our cells, that's exactly what our cells do. They can measure. They measure information. They communicate abundantly, chattering away at each other all the time. And they engineer. What are they engineering? They're engineering us. So we engineer because our cells can. So when we talk about how do cells resemble humans, it's really how humans resemble cells. It's really the opposite. We are, and the term is an epiphenomenon. We're an extension. We're a derivative of all of the behaviors and practices and rules of cellular life. We bring to them our idiosyncratic, our unique ensemble, our human species-specific ensemble of additions. We're like variations on a theme, but the theme is so essential that we never get away. We can't escape the basic theme. All that we can do is we assert it, we embellish it, we manifest it in a slightly different way. So what are cells building? Us. They unite together to build the tissue ecologies that form together the gut tissue ecology, the pancreas tissue ecology, the lung tissue ecology. Then they all work together at the next level, at the next scale, to create us. So what does this mean in reverse? It means that we can use, if we become clever in our research about cell-cell communication and learning about how cells measure together, we can enlist their intelligence towards finding solutions to a vast number of human diseases. The solution of plastics in the environment are probably going to be intelligent microbes and so on. So we're going to have new solutions. We will learn from cells how salamanders regenerate a limb. We don't know how, but we know they can. It's probable that we can too, but we're blocked from it for some evolutionary reason, which is yet to be discerned. But it's almost certainly there in us. And there are researchers that are doing a great job. There's Mike Levin up in Tufts.
I was going to ask if you knew of his work. Yeah.
Oh, deeply. In fact, he and I have talked about it a number of times. He's doing critically important research. We will find those solutions. So we will understand more about the gradients, the electrical, bioelectrical gradients that are part of it. But they're not going to be the only part, because cells use every imaginable cellular-based tool in order to accomplish their problem-solving goals. And so you can imagine the range of products that will be available, solutions to medical conditions. I truly believe that when we learn a great deal more about our microbiome, we will find at least partial solutions to a great many of the chronic diseases that we just regard as, well, I'm just getting old. It just comes with the territory. Well, frankly, we know that there are certain individuals that resist those things. It means that it's within all of us to be like that if we just had the key. One of the things that we're learning in diabetes, for example, I mentioned metformin is modulating the gut microbiome. We know that the microbiome of people with diabetes is different compared to those that don't have that issue. We do know that certain probiotics and prebiotics seem to nudge the microbiome into a productive direction. It doesn't work equally well for every individual, but we do know that in general, that's one additional pathway that is being discovered that can help individuals towards living longer and healthier lives to greater degrees of well-being. We know microbes, and this is almost frightening, microbes in many ways control our behaviors and personality. It's a disturbing thing that microbes can possibly affect whether or not you're depressed, optimistic, your just your general mood, your outlook on life. It seems absurd, but it's true. They produce specific neurotransmitters. Serotonin is almost totally dependent on a partnership between our gut cells and critical microbes. And without those critical microbes, we wouldn't have the serotonin levels that we have. And the serotonin is considered one of those vital neurotransmitters that assures that we keep a stable mental outlook. So we're smart enough now to know that we need to look. We haven't developed all the tools, but we're clever enough and we will. Why am I particularly optimistic? Because I think we will learn how to harness all these things, because one of the things that the microbe, learning more about cell communication and so on, is we'll be able to design very clever sensors. So I have one section of the book that readers may like. It talks about a woman getting ready to prepare for her date in her 70s because, she's young. She's only in her 70s. My goodness. I mean, it's just nothing. And she's looking into a mirror, and the mirror has a constant set of sensors that's assessing her general health. And it seems that must be science fiction, but it's not really. I'll tell you why. You can't see it, but I'm surrounded by a microbial cloud. I've actually got cells of my own body cells are floating around. It's an invisible signature, and it's very particular to me. And how can I say that? I mean, I can't see it. So first of all, it can be measured with sensors now that we have. But also, everybody's watched the movie where the bloodhounds track the guy that ran off the chain gang. I mean,
that's Cool Hand Luke, right?
Those are old. Yeah, all these old time movies. But
yeah.
What is it that bloodhounds are following? They're following your cells. You're leaving a trail of cells, billions of cells, every day. Everywhere you go can be. If you were a bloodhound, we could track your every movement. How specific is it? Bloodhounds have the capacity to identify every single individual. So a twin to our eyes could be identical. To a bloodhound, they're individual. The bloodhound can follow a trail for 50 or 100 miles 2 weeks after you've left. It is possible that researchers probably now, it probably exists. I don't have the exact machine, but I've got my hands hovering over my keyboard here. I could probably leave this keyboard for a month, and researchers could come back, be sent the keyboard. If they had my microbial signature, they'd know it's Bill Miller.
So this kind of may make some people a little queasy, right? But people should be celebrating it instead of feeling icky, perhaps, about it.
Yeah, no, I in the main, I think it's a celebration. I'll tell you, because it's a tool. Now that we know that we have this kind of specific signature, it means that if we were clever enough in manipulating it, we could get those people that live the longest, that have the healthiest lives, and try to figure out why. So I've loved jogging my whole life. For 50 plus years, and I've been really lucky. I don't have knee problems. I don't have hip problems. And I have friends, wonderful friends, that haven't jogged a mile in their whole life, and
Yeah.
they're crippled up. They've
Yeah.
got total hips, they've got total knees. What's the sense of it? Why is that? Well, it could be. Well, we've talked about blood types. We've talked about luck. We talk about micro trauma. I'm just a very good runner. Well, that's ridiculous. I'm a clumsy runner, and I'm just a terrible athlete. My only merit is I keep at it because I like it, but I like it because I'm not in pain. So the question becomes, what is that crucial difference? Well, in the ear of the cell, we're going to find out why. And then what does that mean in the end? It means that people will be given a set of options that will allow them to take advantage of some kind of modulation that will give them a better shot of health and well-being across their life, and probably a, a good deal longer life than ordinarily. What has been the result of each of the prior great medical revolutions? More and more of the population gets a fair shot at a healthy, happy life. Take something as mundane as eyeglasses and contact lenses. Well, I have poor eyesight. I'm wearing contact lenses. Guess what? I'm even. In another era, I would be the blind guy in the village. I couldn't have hunted. I couldn't. I mean, I could. I would walk into the tree. I couldn't see a game to fire or something, a bow and arrow or a gun or anything. Um, I'm not suited for survival. So, given glasses and contact lenses, in that respect, I'm even. It's the same thing with someone with heart failure. When people devised digitalis a couple of hundred years ago, they started to find means of making people a little bit more even when they might ordinarily have died prematurely. Same thing with smallpox vaccination and so on. Treatments for TB. The end result of each and every single medical advance was a greater and greater possibility for each individual, each average individual, to lead a healthy, happy life. Not everyone gets that, but better and better probabilities on the whole. And that comes out with improved life expectancies and so on. What will we get from the year of the cell? We'll get a much better overall life spinning out the next several decades. We will find the chronic diseases that I mentioned, rheumatoid arthritis, diabetes, hypertension, all of them will be either treated much better than they are today, or they will be cured. And so you'll have a better shot at a longer, healthier life. What else is one other further ramification? So we've talked about engineering. That'll be bioengineering. There'll be bioengineered products, combinations of some kind of a synthetic manufactured lattice and actual cells that are working together in some kind of very intelligent way, almost like an intelligent robot. That will help. We talked about the possibility of regeneration of organs, regeneration of brain cells, all sorts of things like that. There will be much improved treatments for inflammation. Chronic inflammation is one of the major causes of disease. There's no question that microbial dysfunction is one of the chief causes of this kind of inflammation. So if we learn how to tune our microbiome better, we learned how to cut down on inflammation. When we use probiotics and prebiotics, what's the common denominator in most instances? They improve what's called inflammation. They just bring down the general level of inflammation that is part and parcel of stress. And that's one of the great killers in modern society, is just simply stress. And that breaks down cellular activities. So what will we need to do to deliver this? A new way of looking at medicine. So if you go to the doctor, you have hypertension, the doctor is going to give you the range of pills for hypertension that almost everybody gets. It could be thiazides, the things like that, or it could be a beta blocker. The thing is, you're going to generally be approached as one size fits all. In the future, we will have your personal signature, some kind of an assessment of your metabolic profile, which is very different from the crude way that we go about it today. and your microbiome and smart programs, computer programs, will devise the probabilities that any one of these medications will work well for you. So what will be the first thing that will be used? The first thing that will be done is they'll try to adjust that microbiome so that you fit the profile of people that don't have this problem. Pharmaceuticals, rather than being the first thing you get, will become the thing that you get when the other thing didn't work. It's a complete reverse of where we've been in the past. And if this seems pretty far out, it's not as far as you think. If we gave as much emphasis to understanding our cells as we do trying to put somebody on Mars, we'd get a long way there much faster than we're ever going to get to Mars, because we're not going to Mars. I'm sorry to have such a long answer, but for me, it's the most exciting topic in the world.
Could it be that, so let's say I buy your premise that we're going to treat first line using microbiome adjustments using microbes. Could it be, and given that we have our individual signature microbiomes, and yet, so it could be seen as somewhat miraculous that we have health at all because there's so many different interactions going on. But your premise is that these cells are working intelligently together. So could it be that there's a robustness and wide range of self-organization that fits within a healthy profile, so that it's not that big a worry that introducing some set of microbes will throw off the whole system, right? Because it sounds a little scary mucking with a system that has evolved over millions of years to be in this sort of nice cooperative state. And mucking with that sounds somewhat challenging or scary, I suppose. Could sound scary, but could it be that the range of healthy interactions is just so wide, the space of possible healthy interactions is so wide that there's a robustness there that might soothe our concerns?
Absolutely. That's a great way to look at it. We are blessed with resilience. It's true with all living things. They're remarkably resilient to stress. And so when I say that cells are problem solving and that they band together to solve problems together, it's true. But there are lots of solutions to problems. Why are cells so intelligent is because they can see more than one solution, and they take advantage of more than one solution, given the opportunities, the tools that they have available, given the substrates that they have. So in cellular terms, if they don't have the proper nutrients that they're accustomed to, one form of let's say you take a certain microbe that's used to a certain form of glucose. Well, you give them another form of glucose, another form of sugar, and they'll make a metabolic switch. The genes are tools. Yes, genes are crucial. They're absolutely vital to whom we are and how we live and our lifespan. They're important contributors in ways we don't understand yet, but they're just tools of the cell. They're memory. We've had an 80-year romance with genes, and we almost everyone assumes that your genes control your life. Well, the era of the cell says no.
Yeah,
genes are vital tools. Yeah, it's because they're not masters. As if you take a gene and you take it outside of the cell, it's inert. It has no effect. It is the cell that is the problem-solving entity. It's an organized whole. And this is an important point because that's what all this research is that we need to do together, the concept of the organized whole. I suppose someone else would call it holistic, but it really is. It's in the connections. It's in how all of the parts fit together. If you do a reduction, and you reduce it just to the molecules, or you reduce it just to the cell signaling pathways, and if you knew all of those little individual moieties or parts of the whole, you still wouldn't understand it until you truly comprehended how they all link together as an organized whole. This is the vital secret that we'll have to uncover, and it'll take many decades to do that. How is it that the whole is more than the sum of its parts? Mm-hmm. And it's a big debate in biology and in evolution, whether you can possibly understand things through reduction, or whether in doing that you destroy the character of it. And it's much too complicated to go into today on this broadcast. But evolutionary biology and biology have argued about this for centuries. Exactly where does that line lie? And I'll tell you, we don't know where that line lies, but we do know that the reduction will destroy the essence of it. And it's not metaphysical. It's just that we are much more than the sum of the parts. That's also true for human societies. It shouldn't surprise us that a collective action at the level of the holobiont, the superorganisms, the human beings working together, produce things that no individual in and of themselves would ever conceive of or be able to do. Things emerge. They emerge from the processes themselves, the connections themselves. And that's the vital principle that the ear of the cell concentrates on, that Bioverse, the book, concentrates on. We are embarking on a wonderful exploration of all of these connections. And so one of the things that we're going to learn is that we can learn them. It's complicated, but here's a mysterious thing that we don't get. And so you said, is it frightening or not? Well, it's intimidating, but it's exhilarating because, for example, in diabetes, there are young diabetics that do really well. There are diabetics, adult onset diabetics, let's say, that get diabetes in their 30s, and they live happily into their 90s. We don't know why. Why that subset? We know statistically that there are risks for cardiovascular disease and stroke and things like that. But why are those people immune? Why are some people immune to heart disease? Virtually immune. So if there's a village in Italy where the cholesterol levels are sky high, I mean, we're talking about double the cholesterol levels in if you measure the things, they're double. There's no heart disease in that small village. And now, of course, there are genetic markers, and that may have something important to do with it. But there's more to it than the genes themselves. And we don't have those answers yet. So what I'm getting at is, when I talk about individualized medicine, and I'm mentioning that you're going to have much more specifically tailored solutions to your problem, ultimately, decades from now when you go to the doctor. There's one other freedom of action that comes from the ear of the cell. The recognition that your numbers don't have to be perfect. So you get your chemistry 18 back, and my God, I've got 3 stars there, and I'm scared to death. This is terrible. That's terrible. Well, actually, there's another fraction of life there, the connections part of it, that we really don't understand. We just know the book. But the connections part of it is, you could actually be quite healthy and your numbers are not normal, not exactly normal. Again, there's this robustness, this resilience that allows many solutions to the same problem. And so those exact chemistry profiles that your doctor would look at and gravely tell you that you've got something that really is a little bit alarming here and we're going to have to go, that may not be so for you as an actual individual. That's the difference between the then, that was the before, and the future where we're going. It will be much more nuanced, and that will be a certain freedom of action that for example, with the issue of weight, some people just do fine being overweight. It's really not a health problem for them. For others, it's a crucial source of metabolic syndrome, with deterioration, with insulin resistance and glucose intolerance and hypertension and risks of renal failure and all the sorts of things that go with metabolic syndrome. 2 people, they look the same when you're looking at them, but they're metabolically totally different. And that's the difference of the ear of the cell, where we're going compared to where we were.
Going back to the idea of DNA as a tool, so you talk a lot about cell intelligence, and you use words like self-awareness, that cells have some form of self-awareness. And, reading it multiple times in the book, because you keep coming back to the same theme, it makes me wonder how you view our own intelligence. First of all, so what I would like you to do is compare what you mean by cell intelligence and self-awareness to what you mean, to how you think of human or organism intelligence and self-awareness. But then I also want to ask you, do you consider our intelligence as serving cells? So is our intelligence a tool for cells, like DNA is a tool for cells?
Yeah. That's a terrific question. Okay. What does cellular intelligence mean? Well, I mentioned one thing.
Right.
They're problem solving. How do we know that they're self-aware? Well, we know that by observation. What do I mean by that, though? It means that cells are aware of the quality of information. This sounds a little bit iffy, a little bit hard to understand. What does it mean by that? And this is actually a really important point. Cells know that their information is imprecise.
Being is doubt.
Get it. Yeah, they get it. You say, well, Bill, how do they get it? How do they know that? I don't know that answer. I don't even know why cells are smart. I just know that they are, and they have been smart since the first competent cell about 3.8 billion years ago, or maybe more. It could be 4.28 billion at the upper maximum. But the point is, the very first cell was smart in its own way. And what does that mean? It was self-aware. And what does that mean? It means that it knew that its information is imperfect and has to be measured internally. It also means that a cell knew that there are others that measure like it did. Otherwise, we wouldn't have had cellular cooperation. How do we know? How do we know the origin? This will sound digressive, but it'll all work back into one organized whole. I promise. How do we define the origin of life? How do we know when life began?
Right.
Well, an individual cell is not going to leave a fossil. It can't. It's just there's no way for it to fossilize. Every bit of evidence that we have for the actual origin of life is based on cells living together, living contiguously with one another,
right,
which implies absolutely at the cellular level cooperation, collaboration, and codependence. They've traded resources. Why do we know that cells are self-aware? Because they'll trade resources for each other's benefit. We know that in a biofilm, that's the collection of microbes that are living together to improve their chances. And these biofilms are what actually cause infectious disease in humans, not individual microbes. They have to band together before they really become a problem. So then these little microbial cities, these biofilms, these little microbial societies, if there's antibiotics floating around, there might be some cells, some microbes in that biofilm that are resistant to the antibiotic. And that resistance is actually contributed by a viral companion that's living within, and this is how complicated the system is, their own partnership with a virus. It's living inside the microbe. And so this cell can determine to donate some of its genes, some of its, like the viral gene, to a cell that lacks resistance to the antibiotic, the bacterial cell that lacks resistance, so that they can both get through it together. So this is awareness of status. A cell is aware of its own status. That's how it upholds itself against an agitating environment. It measures itself against that environment, and it assimilates the outside, and it upholds itself. It knows that others are like it, and it trades resources freely with it. And so That's how cells are intelligent. That's how we know they're intelligent. We know they're intelligent because of their patterns of behavior, just like we know humans are intelligent by their patterns of behavior. So how would we rate cellular intelligence versus our own? Well, totally different. I really don't think cells have egos in the way we do. I really doubt that they have abstractions.
They don't deliberate.
Yeah, I mean, as far as I know, they don't get on Tinder and try to attract their mates. I mean, it's just they live at their scale. But here's our error: we regard our intelligence as intelligence. It's
right.
So look back at Darwin. When Darwin was writing his crucial text in 1859, it was very Victorian era. So what is Darwinism? It's not wrong, by the way. Darwin said two critically important, smart things, and deserves the high regard that he has as a scientist. But it was still a very Victorian era, and so it was natural for the concept of survival of the fittest to resonate with a Victorian male group of scientists. It was the natural order. It's not the way the world actually works. The world actually works through cooperation compared to competition. Yes, competition is fierce. It's obvious. You go on the Serengeti plain, you're going to see it, but you forget that when the lion is taking down the wildebeest, that's one-on-one, and there's going to be one winner and one loser. But there are hundreds of trillions of cells working together seamlessly in both of them to enable them to exist for this moment, for this final drama. So where's our emphasis on the final drama? Where do we put our emphasis on intelligence? Our kind of intelligence is how we measure intelligence across the scale. But that's not the way biology should measure it, and it's not the way evolution measures it. So who's smarter, cells or humans? Well, it depends. It depends on the test. Stephen Hawking is accredited with saying that intelligence is the ability to adapt to change. He might have said it. I mean, it's not 100% sure, but it's a great way to put it. It is a great way to consider intelligence. And so what does this mean for humans versus cells? Well, cells have been in continuous successful existence on this planet for billions of years. Humans have lived on this planet as our kinds of humans, our Homo sapiens. The estimates are somewhere between 200 and 300,000 years, probably 300,000 years. And it isn't clear that we're going to last another 300,000, given our personal type of intelligence. So who is more intelligent? And what is biology's purpose? Well, it's disturbing, but you got to take the evidence for what it is. If cells have been continuously, perennially successful on this planet for billions of years, then they are the purpose. What are we then? We're solutions to problems for cells, and we explore the environment in ways that no other creature on this planet does, and we bring back information to our cells. We're communicating to them all the time. We're explorers of the planet, and we are bringing information back to those basic cellular lines. And I know it's a very inverted way of looking at things, and it's going to take time for people to let this sink in because it just seems almost perverse. But that's the evidence. We are cellular beings, and our major purpose is exactly to be that, to be cellular beings, and to return information back to the perpetual cells that dominate the planet.
That's a shot to the ego, though.
It's terrible, but here's an interesting thing. Here's an interesting thing we're doing. So this is just a thought experiment. I'm not saying this is absolutely correct, but it's part of the evidence that exists. You just have to work with it. So I've told you that cells are engineers, and I told you that we are what they've engineered. We and every other creature that you can see with our eyes. I mean, we're not exceptional in that regard. We're just another engineered habitat. This is crushing to metaphysicians and many religious people. And actually, I don't think it's any argument against religion. It's just simply a different way of looking at it. It is possible for us to consider that how clever ourselves. Could they be clever enough to create humans that are clever enough to send them into space? To give them an opportunity to explore the next environment beyond the planet. Now, you say, well, that's absurd. Well, you say that, but think of the evidence. We've done it. We have sent microbes. We didn't even know we're doing it. You know, NASA had its clean rooms back in the 70s, and they were scrupulous about trying to make sure that there were no bugs on the ships that went to Mars and the initial probes that went out, Voyager 1 and 2 that are now past the heliosphere, billions of miles away. The idea was that they should be sterile, and they tested them very carefully. And guess what? The technology was lousy. And it turns out they were loaded with microbes. And microbes are adaptable, and some of them are termed extremophiles, which means they can actually survive in conditions that no human could even bear for a minute. Temperatures that are well below zero, enormously below zero, or frighteningly high. They can endure radiation that no human being can. They're just some of them, not all microbes. Some of them are very fragile, but a lot of them, many of them, especially those that are everywhere on the planet, including miles down below the Earth's crust or up in the stratosphere, they're everywhere. Some of them are very hardy. Inadvertently, we've sent them out, and so maybe it's not an absurdity to say that how smart are microbes? Clever enough to have us send them out. Now, I'm not saying that's true. I'm just saying it is one way to interpret exactly what's happened. And there's no way to say absolutely it isn't true without misunderstanding the particularities of microbial intelligence. Our intelligence, and Darwin actually saw this too. Darwin was aware. He really didn't think that he was thinking of animals specifically. He had a very pluralistic viewpoint. He felt that it's a different manifestation as opposed to kind. And I happen to agree with that. I think that our form of intelligence is its own specific, I'd like the word, idiosyncratic manifestation of all of the cellular proclivities. And we also abstract things more. I think we have an emergent property that is different from certain other animals. But here's the other disturbing thing. Plants are highly intelligent. They are not, just because they don't move and just because we don't communicate with them in the ways that we think the ways that we consider to be communication.
Yeah.
Plants are quite intelligent. They are highly adaptable. They are solutions. They solve problems. They form partnerships with microbes. They form partnerships among themselves. If we really understood forests, you'd realize that what you're seeing above ground is trivial compared to what's going on underneath and all the connections that are bring them together into the complexities are well beyond a human city. So we stand on the threshold of actually learning about this, and I think it's going to be very important. I think it will ultimately impact how we look for extraterrestrial intelligence, of which I'm doubtful that. I mean,
you're doubtful aliens exist? Is that what you were about to say?
Yes, I am doubtful, and except I would say only one thing: if aliens exist, I think they're intelligent, and the reason for that, and I'm stealing this from a cartoonist. How they're intelligent because they haven't tried to contact us. So that's how smart they are. They haven't tried to reach us. I mean, we're too dangerous. We're very competitive as a life form.
But it's we can just blame it on ourselves, though. I'm going to start blaming things on myself,
Yes,
for my own behaviors.
I like. Yes, I wrote an article once about about a love for chocolate, and my microbes made me do it.
My microbes
basically,
yeah,
it was my punchline there.
The term intelligence, though, is notoriously difficult for people to settle on a definition. I mean, you just used Stephen Hawking's definition of to adapt. What was it? To adapt to change?
Change.
Yeah.
Yep.
Which I think is a fairly common, definition of intelligence. It just makes me wonder, do we need different words for, microbial and that kind of intelligence versus our kind of intelligence, right? In any case, I know that you're not an AI expert, but I'm sure you're well aware of the many impressive feats that AI has undergone. And you're talking about the era of the cell. And a lot of people, I think, would say it's the era of artificial intelligence because of this recent revolution, deep learning revolution, and AI boom that's happening right now. Maybe, I'll since I haven't done this yet, I'll read a passage from your book about AI, and then I'd like to ask you, just about your views on AI, given your views on the cell. Artificial intelligence may ultimately produce a robot that is so sophisticated it can easily fool a human observer into believing that it is a living entity. Yet, it will still not be alive. No computer engineer can devise that program without simultaneously understanding how to create life, which is the quote-unquote knowing internal state, a state of doubt. Artificial intelligence will always remain an artful facsimile of living processes, but it will not be alive. So, is life necessary for intelligence, or what's your view on creating artificial intelligence, which obviously doesn't have a microbiome, although the computers probably do, and obviously is not alive? So just 30,000 foot view, how do you view the artificial intelligence efforts, and should it be called intelligence?
I think it should. It is intelligence. It is a tool. Intelligence is a tool. We talk about something as simple as an intelligent thermostat. We simply mean that it assists us in solving a certain set of problems through programming. But here's the distinction in those forms of intelligence. There's living intelligence and there's computer intelligence. And what are the two differences? Well, the very basic one has to do with the quality of information. I'll explain. If you look at Shannon information, that's the basic mathematical construct that's used for computers. And there are many different types of computer intelligence. There's algorithmic intelligence, information, and all sorts of things. But basically with Shannon information, it's data, it's bits. And if you look at the waveform, if you look at in your mind's eye and you consider a waveform in a computer, the data spikes. It has very sharp margins. It's a 1 or a 0. It's triggered or it's not. There's no actual nuance within the flow of information. It's the computer program, the computer logical processor that creates any nuanced answers that comes out. But the information itself is definitive. Its edges are sharp. Well, so that's totally different. In biological information, it's completely different. And never the two will meet right now, because in biological information, it's a curve. It's a sine wave. And that curve means that the information doesn't have sharp edges, it has ambiguities. And that's living intelligence. Living intelligence is knowing that the data is imperfect. I don't think any listener is going to say, oh, my computer knows that the data that it's gotten is corrupted. It doesn't know it. It just stops. It's completely qualitatively different. Living things, even cells, know the quality of their data is limited. And that explains biology, and that's the Bioverse, the book explains to you why that particular principle is so crucial to biology. So what does that mean with respect to the concept of an AI that's alive? Well, the programmers would have to figure out how to create that sense of internal knowing. But here's the problem. We don't know how that's done. We don't know why that is so within cells. We don't know why that's the living principle. Hence, if you are able to do it as a computer program, you have created life. And I'll tell you, there isn't the slightest prospect that that's going to happen. I mean, that's talk about science fiction. That's way out in the future.
But you can design probabilistic programs, right? So, even deep learning.
Yes, completely, yes.
Yeah.
Yep.
So it comes out with probabilities, and then you softmax it to pick the right answer, right?
Yeah, exactly. But it never overcomes. So an intelligent, nuanced human designer figures out a program that allows a computer that knows no doubt to mimic doubt, human doubt. So I was talking with a colleague, and I said, he asked me about the Turing test. The Turing test is the concept by the genius Alan Turing that we would consider a computer to be intelligent if it could fool someone into believing that it was another living person, a person that wasn't seeing the computer but having a conversation with it. And if the conversation was so satisfying, computer to human, that the human thought it was talking to another human, that it would have passed the intelligence test. Well, it would have definitely passed the concept of intelligent computer programming test. And there's any doubt in my mind that we will create AIs that are so intelligent that they will routinely fool even very perceptive people into believing that they're alive. But it will simply be a facsimile. It will be basically an engineering feat, a trick, because that being that you're talking to is still programmed, and it has no doubt. It won't be irrational. You say, well, we could program in irrationality. No. Part of being is doubt. Part of ambiguity. Part of uncertainty is that sometimes you do the thing that doesn't make any sense. We each do it.
Not me.
We know we do it. Actually, our cells do it less than humans.
Oh, okay.
And animals are much more sensible. In fact, I like to say that the thing that separates us from all other animals is that we're the only one that's capable of actual irrational action over and over again. We are. It's almost a form of intelligent perversion. We will sometimes do the craziest things. Even if a panther could figure out how to skydive, it wouldn't. It just wouldn't do it. There's no panther that leaps out of a tree to the ground and says, "Oh, I just did it for fun." It's just not how they, as an intelligent collection, a collection of ecologies, of cellular ecologies, they're just not put together that way. That's not their form of intelligence. I really do think we have a very specific form of human intelligence. I don't think we understand it very well, but I tell you absolutely, it is nonetheless absolutely derivative of cellular intelligence. And trying to understand it means we have to understand how we are that special combination of cells that enable us to engineer better than any other creature on the planet, and to do so in ways that are highly clever, utilizing abstract thought in ways that other animals and plants can't.
You're not worried about a super intelligent AI taking over the world and destroying us and stuff.
I think the possibility of aggressive AIs certainly exists. That's obvious. No, again, it would have to be programmed. It would be the individual behind it that is the force. The computer itself is not going to do it.
And therefore, it's the cells. The cells will have made the AI that takes us over.
Here's a possibility, and actually this is being worked on in labs already all over the world. It is possible that I'll be contradicted about AI insofar as it will be a synthetic combination of living cells that are part of a computer matrix and done in a very clever way that I can't currently imagine, but I think it's conceivable that you could get that quasi-living combination that somehow leverages the living circumstance of being as doubt with the precise information utilization of a computer, and together it becomes a different kind of life form, a living synthetic life form, and that possibly could satisfy. But again, that there would be some living thing to it. It would not be just a computer in and of itself.
Right. Yeah, these sorts of ideas are rife for science fiction, and I've had a few of these ideas. I need to get writing. But so, okay, and I know you're not a neuroscientist, but so a lot of what we talk about here on the podcast is so AI is interesting in that its birth was really because of what they knew about neuroscience at the time. And like the units in deep learning networks are inspired by the neurons spiking, artificial neurons, right? Make up these layered deep learning architectures. And right now in computational neuroscience, there's a lot of excitement and work being done using the deep learning architectures and AI architectures to try to understand how our brains are functioning the way that they do. Do you have thoughts on whether that is a wise or prosperous endeavor, or would we be missing something crucial by analyzing our own intelligence using the intelligence of the artificial systems that we have built?
No, I think we can leverage all of our tools. I don't have any problem with that. I would say that there is one major obstacle in neuroscience research. It's not universal. I think it's beginning to break down from a prior prejudice, and that is it's natural that you start with the concept of exclusive human intelligence, and you begin with the concept that only humans are intelligent. That was a big prejudice for a very long time, which is fading.
Yeah, true.
It wasn't very long ago that it was absolutely believed, and we're only talking decades, that only humans had real intelligence. All other creatures were just basically robust automatons, like really fancy robots. But anyone with a dog knows that dog's intelligent and has feelings and has emotions.
Not my dog, but okay.
Well, my dog did. What's wrong with your dog?
Dumb as a rock. I'm sorry. We love her.
No, my dog was pretty stupid too, but she was very sweet. And she could be smart at certain moments.
Sure.
But certainly emotional. Absolutely very emotional. Maybe that was one of the reasons she could be annoying.
My dog recycles her own biome quite a bit.
Oh no!
Yeah, it's awful.
I think I know what you mean. Yeah. I think I know what you mean. My sister has that same dog. My!
Anyway,
she's been unable to break it too.
We've given up. Yeah.
Oh goodness. Anyway, so the neuroscience approach had been from top down.
Yeah.
You take what you know about human intelligence, what you believe about human superiority. And then you believe further that only humans have real sentience. So there's consciousness, there's cognition, and there's sentience. None of them are formally defined. No one really understands what consciousness is. No one. We're all working to some kind of common definition. But here's the thing that I and my colleagues insist upon in a book we're writing. For Oxford University Press, that all cells have all of the capacities that we grant ourselves. They're cognitive. That means they measure information. They're aware of those measurements. They are sentient. They don't have feelings the way we have feelings, but they have states of preference, which is why bugs go to the same spot in the human body over and over again to wreak their particular havoc. That's why you can get liver disease, and viral infections of the liver, or viral infections of the brain, or Haemophilus goes to the lung and very rarely goes to any other body parts, and so on. There are bugs that go everywhere, like TB can notoriously go everywhere, but it tends to affect lungs more than anything else. So cells are sentient. And I think in order to actually to create a robust program, it's not just humans top down and trying to work from the point of view on how computer programs can help us understand human intelligence from top down. I think that if you use that computer programming and you work hard to figure out how it cells up, that's how it's cellular, the basics of cellular intelligence work their way into human type of intelligence, I think it would be more productive. Let me explain one specific aspect in support of that. I'm sure you know about the hard problem of intelligence.
For those that are not consciousness?
Of consciousness, yes, thank you. For those that are not familiar with it, you can consider consciousness into two kind of aliquots, two types of portions. There's one portion which is called by a brilliant guy named Chalmers. It was called the easy problem. That's how do we know that something is cold or hot or fast or slow or bright or dark? That's connections. That's like the quantitative aspect. Enough information reaches us, we assess it as a specific experience. But then there's another realm of experience, which is much harder to define. So, for example, if I hit a hammer on my thumb, I see red. You heard that expression, to see red. What is that? Where does that come from? That seems very much more mysterious. And that's called the hard problem. And this has really seduced a couple of generations of neuroscientists. It seems like a terrific idea. The only problem is there's no reason for it. If you understand that cells are intelligent and why they're intelligent, then you realize that that's just a human way of categorizing things because it's satisfying. But cells have all the apparatus for feelings of all different kinds. They're surrounded by an intelligent membrane, the plasma membrane, the outside of the membrane. And every single bit of information that can come into a cell, that a cell has to go through it. So a cell doesn't know one bit of information that it hasn't produced. This is a difficult concept. What do I mean by that? And a surprising conclusion comes from this. There's no way that information can go from outside of a cell to get to the inside of a cell without crossing that membrane. And there's no way any information, any environmental cue can reach a cell without a delay in time, having to travel through the separations between cells and the fluid matrix that's between them, and so on and so on. All of those things create information degradation. It's noisy inside a cell also because it's a very packed environment filled with tools for cellular life. So that's part of this information ambiguity, this doubt that I'm talking about. The cell never gets perfect information. If there was a perfect source of data, they could never know it. And the only information they have always has to travel across all of these barriers, get through the membrane, the plasma membrane, and then get inside and get measured through an internal process, which is itself noisy. What does this mean? It means that a cell is producing the actual information it has. It's derivative of what's on the outside, but it is self-generated on the inside. A cell only knows what a cell produces, the information it produces, the derivative information that it produces. This is not conjectural. This is an absolute requirement of cellular life. Just go look at a cell. It's actually quite obvious when you look at it. What does that mean? It means that we ourselves, as human beings, are a constellation, an enormous constellation of self-produced information. There is no external absolute reality. It's only our interpretation of it. We agree on what reality looks like is because we're all species human. We're all humans. So in general, we all evaluate all external cues in a self-similar manner. This issue of self-similarity is really important. Why do we know that cells are intelligent? Because they know that others experience things in the same way and they'll trade resources because of it. What does that mean for us? We internally devise our own world, our own reality of external informational inputs. And as it happens, because of our architecture, our information management systems, to human, they're all alike. We tend to produce the same interpretation of reality, except for the small minority of us that don't. And they're always the people that we say, well, he lives in his own world. What can I say? He sees it differently. I mean, you always shrug, but there's a real good reason for it. It's a condition of life that can never, ever be otherwise. So your interpretation of reality is exactly that. You don't have a connection to the external reality that's any more robust than the next person. You may agree with the next person in general construct, but each cell constructs its own reality, and then it communicates that to other cells, and together they average these things. That's a wisdom of crowds, and they produce biological outputs. That's us. And what do? We take the us, ourselves, and then we agree on a certain set of reality, and we form collective actions. We engineer together, we build buildings together, we have collective societies, we institute governments, and we don't get along with each other because we're all living on our own reality. And this is not even conjectural, it's just basic biology, but we just didn't know that until a very short time ago.
The book is Bioverse, How the Cellular World Contains the Secrets to Life's Biggest Questions. And we touched on, a few topics from the book, but we only skim the surface. I mean, you go into quantum effects in biology and populating the universe with our microbes and just tons and tons of really well-informed examples of our microbiomes and different kinds of microbes and how they affect our cognition, and not just through the gut. And like you mentioned before, how our brain, which because of the blood-brain barrier was thought to be completely sterile, has its own, although smaller, microbiome, which I don't know how to think about that, whether that's good or bad. But anyway, I hope that people check out the book, and I appreciate the conversation today. Thanks for being on.
Oh, it's been a pleasure. Thank you very much for having me on.
I alone produce Brain Inspired. If you value this podcast, consider supporting it through Patreon to access full versions of all the episodes and to join our Discord community. Or if you want to learn more about the intersection of neuroscience and AI, consider signing up for my online course, Neuro-AI, The Quest to Explain Intelligence. Go to braininspired.co to learn more. To get in touch with me, email paul@braininspired.co. You're hearing music by The New Year. Find them at thenewyear.net. Thank you for your support. See you next time.